we have seen the sudden expansion, right? Sudden expansion. Now let's now think about isothermal and adiabatic expansion. So what is isothermal? Isothermal expansion is easy to simulate. Should I start with adiabatic? Maybe I should start with adiabatic. Maybe I should start with isothermal and adiabatic expansion. No, let me start with isothermal. Okay. Isothermal is easier. Okay. Isothermal expansion is simply this. You have a box, right? You think of this wall as a side of a piston, and you start moving this with a slow velocity. Okay? And you keep the rest of the code the same. Let me show you. Let me show you. I have the same stuff here, the same entropy calculations and whatnot. Only after T is greater than 200, so after some thermalization, I start having this velocity, VLXP, meaning that velocity of the right wall is 0.01. And you can see that LXP increases by VLXP times dt. Does it make sense? No? Yes? Are you completely lost? So I really don't change anything else. You might think that, okay, this is a little bit changed, but really not. It's really the same values and the same thing. I only add this expansion to one side. Let me show you what happens when I do this. So I have some thermalization at the beginning, and this wall is not moving, okay, before the thermalization. Then I don't know if you can see it or not, but it starts moving. Did you see it? Yes? So it's moving very slowly. And what you have here is entropy, and what you have here is temperature. Temperature is constant. Entropy is increasing. Why entropy is increasing? Volume is increasing. Very good. Volume is increasing. Volume is increasing. Temperature is the same. Entropy is increasing. More states to cover, etc. Do you have any questions, comments at this point?
If temperature will increase, the entropy will increase too?
If temperature what? This is isothermal process. So temperature is the same. How can we be sure that temperature is the same? Well,
energy is the same.
Energy is the same. The thing is that I didn't change any code, so what happens when it hits the wall? Okay, let me ask you this way. You have a gas and you are pulling a piston. What do you expect to happen? In normal daily life, imagine. Cool down, right? This is not cooling down. Do you realize that? This is not cooling down. This is the same temperature. So I'm doing something unnatural here. And I went crazy about it back in the, like 5 years ago or something. I couldn't find, and the day that I was going to describe this effect was closing. Professor Jamal Yalavik told me what was wrong. You see, gas molecules, gas atoms move at 500 meters per second. 500 meters per second. while I'm pulling this like with 1 millimeter per second, right? Like this. Nevertheless, the ones that are hitting with 500 meter per second, since I'm moving the wall ever so slightly, when it hits it, now let me increase this. You hit a ball and to a tennis racket that was moving like this. What happens to the ball? It doesn't just bounce back with the same velocity. Its bouncing back is decreased. So the gas molecules that are hitting the piston are losing their velocity ever so slightly, but that is enough for the whole effect to happen, the cooling. So why is it cooling? Because, yes, I'm doing work on the system. I'm doing negative work on the system. Yes. Does it make sense? Yes? But do I have that effect here? No. No, because I'm not taking into account the velocity with which I'm moving. So whatever comes, I let it bounce back with the same velocity. So that's why it doesn't lose any energy. But normally, if I'm doing it with piston, that is not the case. The reality is that the gas molecule comes, hits, and slows down. But since I'm putting it back, it means that I'm actually, this simulation, is actually corresponds to isothermal expansion, whereby you keep the temperature the same by heating it. So you pull the piston, but you are also heating it so that the energy that the atom loses is put back. Does it make sense? Every time the atom loses energy, without it losing it, I give it back. So it's isothermal expansion. And in the isothermal expansion, entropy increases. So far, so good?
Is there an example of isothermal expansion in the nature or without heating it by itself? I mean.
Yes, human beings heating it up. Like we are part of nature. So no, I understand your question. Yes, you can have an isothermal expansion if your system is connected to a large heat bath. Do you see? Like you are doing the experiment inside a tank, and that will be naturally the case, and your system is not isolated or whatever. So the temperature is kept fixed, but you are pulling it out. So what you are doing to the system is you are increasing its entropy. You are giving it more space to live, and it increases the entropy. What?
Vacuum chamber. Keeping the constant heat, constant temperature. You don't need to be just extract the vacuum in a balloon, in a vacuum chamber.
Uh-huh.
Then it's isothermal. You don't have any heat. It doesn't cool down.
Why?
Why it cools down? Like you just vacuum out the air,
Mm-hmm.
and you just a balloon. Then the balloon didn't do an isothermal expansion
Mm-hmm. So you have a balloon
in a vacuum chamber. Then you just
pull out the air from the balloon,
vacuum chamber, not the
from the vacuum chamber. What is our system? Is it the balloon or?
balloon.
I see. I don't know. I'm really concentrated on this. And are you okay with what I've explained so far? You have several questions. So let's go like this, okay? Or this is your first question, I think. Yes. Oh, yeah. 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 Yeah.
If the system is it's losing energy because of the piston, and we are gaining this energy by heating up, then why the temperature
No. Why the temperature?
is not like zigzag?
Yes. Yes. In all these codes,
Uh-huh.
the most unphysical thing that I'm plotting is temperature. Why? Because I'm cheating. I'm using thermodynamics stuff. I mean, everything else is derived numerically, except for the temperature. I just sum up the energies. However, that's not the case. Why? Because temperature is only defined for an equilibrium system. Although this goes around in the non-equilibrium state, because I'm not doing it with zero velocity. So you shouldn't really trust that flat line of temperature. It's not a good definition of temperature. And besides, the way that I treated temperature is the way that engineers treat the temperature, meaning that temperature comes first, then entropy is derived from it. But entropy comes first, then you derive temperature from it. That's the right way of treating, well, that's the physicist's way of treating. Which is the right way.
You can define like temperature for anything that you want, even though it's like black
Yeah,
temperature.
I mean, the main problem here is non-equilibrium. Like, temperature is not the same throughout the system. Your question is? Yes, because I'm doing it slowly. Yes, I'm doing it slowly, so there is no... Okay, it's not mine. There is no new information generated which decreases my ignorance. So I'm doing it slowly so that I don't get a new information. Does it make sense? Yes. So it was not a sudden process. Yeah.
Is this process only isothermal, or it is isothermal and adiabatic?
Okay. Coming to adiabatic, I thought that only I am confused with that word.
It's just isothermal.
But no. The problem is the word adiabatic. Okay, it has a different meaning for engineers, different meaning for physicists, different meaning for chemists. So let's just leave it all together. Like, it's a slowly moving isothermal process. Okay, let me call it quasi-static isothermal process. Okay, because physicists, I think, use adiabatic for a specific kind of thing where you don't change the entropy. Do you see what I mean? Because in engineering, I am an engineer as an undergraduate. We thought of it as adiabatic is quasi-static. Adiabatic means quasi-static, meaning that you can have an isothermal process, but if you do it slowly, it means that it's also adiabatic.
Also, there is a meaning of adiabatic, like there is no heat transfer.
Yes. So it's complicated, but I'm sure that it's isothermal, and it has been done slowly. Despite it being done slowly, since I increase the volume, the entropy increases. Yes?
This textbook defines adiabatic process as one which no heat is added or taken away, and isentropic as adiabatic and reversible.
Okay, that's another thing. The fact of being reversible. So isentropic is adiabatic and reversible.
And here I think it's not adiabatic because since we are losing some temperature, since we should be losing some energy by the heating of these, we are adding heat from that right wall to keep the temperature constant. And since heat is added to the system to keep temperatures constant, it should not be adiabatic.
So at the end of the day, it's quasi-static but not adiabatic. Okay?
The entropy is increasing. Just look at the entropy. Entropy is not constant, so it's not adiabatic directly.
But that's not the case for others. Okay. People. If I plot the entropy you can see that it's increasing, right? Hopefully. It's not increasing much, but it's increasing.
Can we increase the volume, the speed of movement of this wall?
Yeah, but I'm afraid a little bit because I might create some problems. So I increase it twice. What do you expect?
In here, the increase of entropy has been very small and it was not statistically significant. I thought if we made the change of the wall faster, then we can see how entropy increases easier.
I see. Shall we call it? We don't have time and just. Yeah, I'm worried about some stuff here because you know. Do you see a better increase already?
Yes.
Okay, that's all I needed. So I can move on. Very good. Now, let me go to adiabatic expansion. This is so what I do. I just comment out this one, and I actually do remove that energy that I'm supposed to remove. Let me show you how. So now I'm at adiabatic expansion. So the ball, let's say it comes with V, and this is a wall that is moving with V wall. What happens is that in the reference frame of V moving with V wall, this one is coming with V minus V wall. V wall, and this is not moving. Do you understand it?
Yes.
So it should go back with V minus V wall. But now let's put back the original velocities. So I have to
V minus 2 V wall.
Yeah, I have to add V wall to everything in the right direction. So I get my original V, I get my V wall, but this one gets V minus 2 V wall because it's going in this direction and I'm removing V wall in this direction. So it's this one. Does it make sense? No, it doesn't? What if the wall is moving towards it? Maybe that's better. If it's V wall moving in this direction, not only it gets the V wall of the V wall, but it also gets V wall because it was moving towards it already. Okay. In any case, this is how you include it. Okay. So for this one, it has to be greater than V wall so that it hits it, right? It's not greater than 0, the velocity. The velocity has to be greater than V wall because V wall is going like this. If it's slower, then they will never collide, right? But if it's faster, so this one is going, do you see? Okay, very good. So this is supposedly going to be the isentropic process. Ready? I mean, drawing this is really unnecessary, but anyways. Do you see the temperature starts dropping? It was constant before, but now I'm taking little by little that energy that the atoms have, and the temperature is decreasing, while entropy, besides the noise, the oscillations, hopefully is not decreasing. Well, it's not increasing, right? I have better calculations coming, so if you are satisfied by this, we can move on. So do you see the difference between isentropic expansion, let's call it that, isentropic expansion and isothermal expansion? Are you happy?
Yes.
Well, as you can see, the next subject is Carnot cycle, right? Do you remember it? Regrettably.
Yeah, it was hard.
It was hard. Okay. Hopefully, this will make it harder. Let's talk about Carnot cycle. What is it? Let's remember it. What do you do in Carnot cycle? If you plot T versus S, you start over here, let's call it 1, and you move to the stage 2. And what is this process? Isothermal expansion, right? Isothermal. Should I write the whole thing? Isothermal expansion. What is this?
Isentropic.
Isentropic what? Also expansion. Right? Because it corresponds to, I mean, the 1 to 2 corresponds to putting heat into the system and keeping the temperature the same, right? No. Yes, yes, while the entropy increases, the thing that we did first, and then going down is the thing that we did second, right? Then there is 3 to 4. What is this? Isothermal compression. So how we can simulate it?
We are compressing it, but with a colder heat bath there, so we are taking the excess heat out.
Yes. So we actually don't change any code. We just flip the velocity of the wall, right? Otherwise, it's still the same story, because as you can see in the code, it already takes into account whether the V wall is positive or negative. I mean, if it's negative, it will be knowing that the velocity is coming like this, and the ball will collide if its velocity is less than that much. So if it's just staying still, it will collide with the wall because the wall is closing in. Does it make sense? Good. And finally, isentropic compression. Again, the same thing, but this time we are taking the energy out of the system. No? What are we doing here? Isentropic compression. Heat it up, right? Okay. Giving energy to the system by doing work. Is that right? Okay. Okay. This is Carnot cycle, and we can actually simulate it. So what do you expect from Carnot cycle? You expect TS diagram to look like a rectangle, right? But all this is presumed to be reversible process. Now, our process is not reversible because imagine this. Normally, you have 10 to the 23 atoms, lots of atoms to thermalize the system, and the wall is moving like millimeter per second while they are moving like 500 meter per second. Here, they are moving with like at most 5, and I'm moving it with 0.01, and there are only 200 atoms. So cut the system some slack, okay? It will not be reversible. All right? All right, very good. So let me see how Carnot cycle was implemented here. This is this. Same system, number of balls. I think I've decreased number of balls. V vol is 0.01. Oh, I have increased this one. Okay, no worries. Everything is fine. I've increased, for example, Q so that I don't have too much oscillations in entropy, because the entropy change will be so small, as you said, that we will not see it if we don't increase Q. Okay. Where is it? Okay. First of all, I thermalize the system. I run it for 1,000 steps and I get it thermalized. I write thermalization complete. Then I have these stages. Where am I at this stage? Like, am I at this stage, at this stage, at this stage, or at this stage? Okay, let me give them numbers. So when I'm at 0 stage, 1 stage, 2 stage, 3 stage. So what happens when it's 0 or 1? The wall is expanding. It has VLXP is V wall. So it's expanding here, expanding here. What happens otherwise? The wall is compressing, getting compressed. What do we have down here? We have at stage 0 and stage 2, 0 and 2, we have isothermal process, right? Otherwise, we have adiabatic or isentropic process, expansion or compression, doesn't matter. Okay, should we wait and run, or you can see the result? What?
Does this also have animation?
No. Do you want animation? Sorry. Sorry. It runs for, I think, 2 minutes, but let's say it ran. Okay, this is what you get. So this is entropy versus temperature. So you have expansion going down. This is our rectangle. Okay, I mean, it doesn't look like anything, but we are working with small number of atoms. Then again, you could wait for longer and you will get a better rectangle. Okay. But as you can see, it doesn't come back to itself. There is certain increase in entropy and certain increase in temperature. Indeed, let's run it for more than 2 cycles, and I mean, it will run for 10 minutes or so. Let it run.
Can you show the diagram again? TS. I would like to ask.
I just erased it. So let me show you for the other one. In the meantime, let me. Yes. Okay. Tell me.
Just go back to the stage 0 when they cross. Then it will be a cycle. Did you understand?
Like when it is crossing.
Yeah. Just do it. Just go.
But what is the fun of that? I mean, what we are going to get is this. It's going to go like this, 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 and then it will go like this, 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 and like it will keep creating more and more entropy, because what we are doing, and it's going to get hotter and hotter, because it's an irreversible process. The way that we do it is irreversible. Okay? That's one thing. The other thing is PV diagram. Okay? And that is your homework. So let's remember the PV diagram for this. It looks like this. So when you go from 1 to 2, it's isothermal expansion, so P times V is equal to
P1 times P1 equals P1.
exactly P1 over here. P1 V1 is equal to P2 V2, or in other words, PV is constant. In yet other words, this is when P is proportional to 1 over V. Or let me write it just like P times V is equal to constant. Does it make sense? This is the isothermal expansion. So as you expand the volume, pressure decreases, and P1 V1 is P2 V2. How about this one? Do you remember this one? Yes, what happens then? Yes, exactly. P times V to the power of gamma is constant. And what is gamma? Cp over Cv. And what is our Cv? Do you remember our Cv? It was 1. Do you remember? For 2 dimensions, it was 1. So for 2 dimensions, 1. Then what is Cp? So normally it would be 3 over 2, and Cp would be 1 more, right? In 3 dimensions. In 2 dimensions, since Cv is 1, Cp is 2. So our gamma is going to be 2. Okay? That's your homework. Your homework is just the isentropic expansion, and you will try to show that PV to the gamma is constant and that gamma is 2. That's it. And you have the code. Okay? You just need to run it for longer to make sure that you get it all. And let's look at the PV diagram here. Do you see pressure, volume? Everything looks like in textbooks. Okay? And let's look at it in log-log scale. It's a straight line. Then the slope of the straight line seems to be twice, right? -1, then -2, then -1 again, then -2 again. So everything checks out, and we are happy. It's still running. So any questions? Come on.
Like for curve fitting.
Curve fitting. You can find curve fitting. No worries. I don't know. It depends. It depends how you write your code. Any other questions? Yes. Notes? Yes. Okay. The notes. Because this is called chapter 4 notes. You are asking for this one. Any other questions? Comments? What we have learned? We have learned connection between macroscopic thermodynamics and statistical physics. Okay? It was a long and bumpy road, but we are at the end of it. Let me just see if this calculation. Well, we don't need to. We are waiting for it to finish so that I can show you this, going like this and going like this, going like that. But no.
There is no fixed point because like it goes.
No, it's just. We will come to attractors very soon.
Like, can it be like that? Like, can we talk like because it's also the phase diagram, right? It's also a phase space.
This is.
Can we generate an attractor in TS space, not in like the Lorentz?
Oh, absolutely. Like, just put two atoms in an ellipse stadium. Let them like bounce off each other. Not even ellipse, just a square, and draw its phase space. Probably you will get something nice, interesting. Yeah? You don't think so?
Should be 4-dimensional.
But in any case, what you are saying is true. All these things, thermodynamics stuff, has everything to do with what we are going to talk about later on, which is like you start with a phase, let's say you start with a uniform phase space, you put all the dots, and you start it running. What will happen is that it will morph into thinner and thinner layers of dough. Like it will be like a dough, but it's being mixed up in any ways possible. When the time comes, let me come back to this idea, because it resolves several paradoxes about thermodynamics. Well, if you buy it. Shall we call it a day?
By the way, how are we calculating the entropy in this code?
The same way. The same way. I mean, entropy is the same. It's calculated like this. You don't like it?
All right. Got it.
Of course, in all these codes, we use KB equals to 1. We don't care about normalization constants, right? We just looked at how things change, and they seem to fit.
And you're also using Shannon entities.
What should I use?
There are some other entropy measures, just use one.
What are they?
There is some called
Ah.
all-knowing.
That was my, I mean, not well-formed thought about it. The thing is that I have a very nice formula for temperature. I wonder if I could have a very nice formula for entropy as well, which would not give a bumpy thing. I came up with this by myself, so it might be wrong. Everything that you have seen so far might be wrong. But I think it teaches you something, right? It's microscopics. Yeah. Okay, let's stop here, and whoever is interested can stay until this calculation finishes. If you don't have any questions. No?
What was CP?
CP was, so Q is C times delta T, heat capacity under constant pressure. So CV is heat capacity under constant volume, CP is heat capacity under constant pressure. Does it make sense? How much heat do you need to have to increase by 1 Kelvin when the volume is constant? How much heat do you need to increase by 1 Kelvin when pressure is constant? So these are two different processes. Yes. When it's constant pressure, you need more energy. Let's. The result is here. So PLT plot entropy versus temperature, but this is cold. So do you see? It's like goes like this, goes like that, goes up here and goes like that. So it goes up again. So it goes like this. What? Yes, we decrease fluctuations as we increase Q. So then you might ask, why don't make it a crazy number? No. Yes, it takes more time, but besides that, it's a moving average. So you start blending different stages into each other. Like isentropic process is done, but you are still using that data in the isothermal process. So the representation is misleading then. As you wish. Let me stop here.